Assalamu alaikum students. I hope you are fine and doing well. Uh, Dear student, today is our seventh lecture of our online series is all about basis for a vector space. Dear student, before our today class, we have discussed linearly independent, spanning set, vector space, and subspace. These concepts are primarily quite important to discuss the concept of basis. When I say basis, what I mean to say, dear student, in basis, we are basically minimizing the number of set in vector space or any subspace of a vector space that span the vector space, any bigger vector space. And that what does basis means? Basis can be constructed through let us say number of vectors in any subspace of a vector space V. But dear student, when you impose the condition of linearly independent, that in that set, not all vectors are linearly independent in basis vector. I mean to say a set which is a spanning set, it may or may not have all linearly independent vectors. Yes, it may be possible that a linearly independent vector form spanning, but it may be possible that all vectors in a some set S of vector space V uh, uh, does not basically form a vector space. And dear student, today lecture is quite important. Basically, why I am saying this lecture is quite important because that basis, if you find the basis of anything or any structure, then with minimum number of object you can construct a large uh, any large set or any large let us say vector space. So the concept of basis is mainly related with the minimization of vectors in any subfield of a vector space V. So let us today, our topic of discussion is bases and dimensions. And in bases, we are mainly talk about linearly independent vectors, spanning set, and some examples that relate the basically bases and dimensions. And what does dimension mean? The number of element in a basis is called dimension of that particular vector space. So, dear student, if I recall that two-dimensional vector space, let us say R square, in that R square, basically, we have two elements which are through two element you can construct any element of R square. Let us say the basis in the linearly independent vector or spanning set of R square is 1001, or in case of three-dimensional vector space R3, it is 100, 010, and 001. So, dear student, let us recall the concept and let us start with definition of basis. So, let V be a subspace of Rn. It means it is a one subset of Rn. by the way, the V must be a subspace of R n for some n. The collection of say any vectors that belonging from V is said to be a basis for V if B is linearly independent and span the vector space V. So there are two criteria to make any set to be a basis. It must be that these vector that is basically containing over here, these are v1, v2, v3, and in that we have basically n column vectors, and this is again n column vector, and this is again n column vector. So that is why I make it bold, because this is a vector. It may be n tuple, this is again n tuple, this is again n tuple, and this is again n tuple. So you have a set of R vector, and having each vector is of length n cross 1 or 1 cross n. So these set B will be form a basis for vector space V if it is linearly independent and span V. Basically, uh, if none of these criteria is satisfied, then the collection is not a basis for V. Um, if a collection of vector space span V, then it contain enough vector so that every vector in V can be written as a linear combination of those in collection. As I have discussed with these, that basically bases shrink the element in any collection, let's say B, that only take those elements which are linearly independent, that ultimately reduce the length of this collection of the set. So if the collection is linearly independent, then it does not contain many vectors that become depend on others. So dear student, the how to analyze this question, that basis just give you the right side. It's not so big, but not so big as be dependent. So, dear student, let us to sum up with all these remarks or sort of bullets, number of marks in statement in bullets. We have to take one examples and understand what does I means to say in these bullets. So let us take one example of two set. Like this is one set, is one of these subspace of R square, and this is again one subspace of R square, and both are spanning set for R square. Means to say these are containing, as we discussed lastly, the spanning is the collection of all possible linear combination. So both are basically spanning set of R square. The If you can see over here, this one, uh, first and second is linearly independent, but this one is not linearly independent. What does it means? This is unnecessary vector in this set. So you can omit this element of basically this element of this set in order to make it span set, because this is already linearly independent, and this is also independent two rows, and these are basically form spanning already. So if you can see over here and realize why it is dependent, because this element can be written as a linear combination of these two rest of two elements. So in that case, if we can omit this element, even then we can say these both uh, set span the vector space V. So in that case, dear student, our discussion is transformed in the form of this theorem, which is given in slide 4. Here it is. Let we have n vectors, a set of at least two vectors in a vector space V, if one of the vector in the set is linear combination of other, then that vector can be deleted from the set without uh, basically diminishing, basically disturbing the idea of spanning. While you remove the vector from linearly dependent set without changing the span, it means that minimal spanning set would be linearly independent. So, dear student, we have converging towards the idea of today lecture. It's about basis and basis and dimension. So this is and again one previous theorem of our class which I have quoted over here in order to give you a another important idea how you can utilize this and judge either your vector or subspace form a basis for any vector space or not. Let us take one take one theorem from our last lectures of linearly independent sets. We have k vector in R, and A is basically V1, K1. This is a matrix. Then V1, V2 up to Vk is linearly independent if and only if the linear system Ak is equivalent to 0 has only non-trivial solution. So it is again fall in the case of infinite many solution. So from this theorem we have one corollary. So if you have a k is greater than n, so you have say number of vector in any set is greater than dimension the number of element in vector space R, and then this one is basically linearly dependent. If k is equal to n, that is number of element and number of uh, power of vector space is same, then it is dependent if and only if determinant of A is 0. So, dear student, let us take one example to judge either how our basically any set form a basis. Let us show that the set 1001 is a basis for R square. Dear student, for basis, you must keep always one thing in your mind. You have to check two two things. One is the vector which is given in this subspace of any vector space must be linearly independent. Moreover, this set basically the which is consists of vectors from two-dimensional vector space R square, then it must span a R square. I means to say, if you can take any arbitrary element from R square, then it can be written as a linear combination of these vector, and all when you find k1 k2, all k1 k2 values will be in the form of these arbitrary element of any vector space, any vector space. But here in this case, the vector space is R square. So the determinant of these vector in S is non-zero. So this implies these vector given vectors are linearly independent. No second criteria is to take any arbitrary element from this vector space and write it as a linear combination of the element given in this subspace, that is S. So I can write it and I calculate A k1 k2 in the form of B. So this shows that the any arbitrary vector from let us say from R square can be written as a linear combination of the basis vector, so the vector span the vector space R square. So dear student, in this case we can say both properties which are basically condition of basis to form any collection of any set of larger vector space is said to be a basis for V if V is linearly independent and span V. So in that case, both condition in example 1 is satisfied. So dear student, we can say these elements which are given in S form a basis for R square. Let us come up with another example. how these elements form a basis for are cubes. So, dear student, if you can take the, because they here the number of vectors are three, so k is three, and the r power is three. So in that case, you can see over here k is equal to n. So it will be linearly independent if and only if determinant is non-zero. So if you can calculate the determinant of these three vectors, which is basically a one set S, so the determinant will is always one. So in that case, these element given in this set, which is a subspace of R square, is linearly independent. So you can check with the help of say determinant, or with the help of this equation, which is basically ax equal to 0. So basically k1 v1 k2 v2 k3 v3 equal to 0. So if you can put all v1 v2 v3 over here, if you can look over here, so you can just put all this. I just recall the example which we have solved in our lecture of linearly independent topic of linearly independent. So I just take this. So dear student, if you can look over here, so these I'm sorry, if you can look over here, so determinant is, so I just take perhaps, oh, sorry, this is uh, sorry. If you can look over here, just put for example. Let me finalize this. So, dear student, if you can look over here, so the example should be like uh, 2, it must be 3, then uh, minus 2, then 1, and then 1. So then 8, then 6, and then 0. So let me correct this one. So if you can, I just correct the example. So if you can look over here, so you have to check this either first linearly independent, or if you have to check it with the help of determinant. If you can take the determinant of this matrix, so the determinant will be 0. In that case, the vector is not linearly independent. If you can check with the help of this equation too, where k1 v1 k2 v2 k3 v3, this is also one of the method equal to 0. Since your this is not just 1 0, this is a basically element from R3, so your output will also be from R3. So you just place 3 0 over here, because 0 is not just 1 0, this is belongs from R3. So in that case, student, uh, the 0 will be 3 tuple. So if you can put all the values over here, the equation of linearly independent, if you recall the lecture of linearly independent, so in that case, dear student, you just transform this equation into a system of equation in terms of ki's. If you solve this, you get k1 k2 k3 values. So in that case, you can say this system basically give you the non-zero values of ki's for k. So for linearly independent, these values must be 0. But in that case, if we have solved this, so we get all non-zero for ki's. In that case, we can say the vector given in this set is linearly dependent. But another way to find either this set of vectors from any vector space is linearly independent or dependent. So you can choose the determinant. If determinant is 0, and from that you can also gauge the linearly independent and dependent. So if determinant is non-zero, then you can say the vectors given in any set is linearly independent. If determinant is equal to zero of any element of any set which is a subspace of R3 is zero, then you can say this vector given in this set or any subset of R3 is linearly dependent. So dear student, let me give you another example. So how to check either this system of equation, the subset which is a subset form a basis for vector space R3 or not. So let me give you the, if you can write this in terms of linear relation of ki's with vi is given over here. Let me for a while to on the spotlight. So these are vectors we have to check its nature with respect to basis. I means to say I would like to find either these vectors which are given in this set are linearly independent or either they form basis. So first of all, these are three equations, three vectors in this set. So first method is to find this via this equation k1 v1, this is v1, k2 v2, this is v2, and k3 v3 equal to 0, and just multiply all ki's with this tuple or order pair or order pair, and you will get this expression, and in second, in third, you will get this one, and then ultimately you have to compare the x component with this 0, and second component of this order pair with this 0, and third component of order pair with this. You will get the homogeneous system of equation. If you calculate the determinant of this homogeneous system, you will get 9, which is non-zero. This reflects that you have only one solution, and which is trivial solution if your determinant is non-zero. So in that case, if you can calculate this value, even then the value will be 0. So I just draw this fact from this, the all values will be 0 because determinant is non-zero. So in that case, our vector which is given in this one of the small subset of R3 is linearly independent. So the second step is to find either whether this vector which is given in one of the subset of R3 for span R3 or not. For that, dear student, you have to take one of, let us say, arbitrary element from R3 ABC and write it as a linear combination of given a V1, V2, V3 in subset that's these vectors, that is subset of these R3. So dear student, you just plug V1, V2, V3 over here and solve this and compare the x coordinate with a and y coordinate with another expression in terms of k, like if you solve this expression. So ultimately you will get this one. So you compare x component with x coordinate, y coordinate with second and third, and c with the third coordinate of right hand side. In that case, dear student, if you can look over the system of equation in terms of non-homogeneous system of equation in terms of ki's, to make this system to be consistent, that I mean to say all the values of k1, k2, k3 must be in term of a, b, c. If the all values of system are in term of k1, all the values of k1 in term of arbitrary elements a, b, c, then we can say the system is consistent for all values of a, b, c. If you can look over here, if I can write this whole system into a augmented matrix, so for reducing reduced echelon form, I calculate the reduced echelon form by performing row operation. So I get k1, this one is equal to basically k1 equal to this, k2 is equivalent to this, and k3 is equivalent to this one. So you can see over here k1, k2, k3 values are basically not depend upon k1, k2, k3, but it depend upon A, B, C. So in this case, the rank of a coefficient matrix and rank of a coefficient matrix and rank of augmented matrix are same. So dear student, from this we can clearly um, this clearly shows that the our vectors given in subspace or subset of vector space R3, three vectors form a span a vector space R3. So in that case, if I can write A, B, C and write on the K1, K2, K3 values. So for example, it should not be formed. It is for example. So, for example, if A, B, C are can be written as any arbitrary element of R cube can be written as a linear combination of these vectors, like this one, which is given in the subset, like this subset. So let me check either any element of R cube can be generated through this linear combination or not. Any element of R cube. R cube means to say X, Y, Z. If you can put any element of over here, any arbitrary element here, the right hand side is equivalent to that element or not. Let us say I take A1, B1, and C1. So I just solve this all these equation. I get right hand side is again equivalent to 1, 1. It means that any arbitrary element, you can place any element of R cube, you can generate this element. So we can say the basically the three vectors, this one and this one and this one, form basically span a vector space R3. So dear student, both conditions are satisfied in this for this set three vectors in this set. So these are linearly independent, as well as they form a span for R cube. So these vector base fundamentally are the basis for R cube. So, dear student, this is just the idea to check spanning. So, let us take one another example that whether the set of given in this vector form a basis for vector space or not. So, we take any arbitrary element from R cube and written as a linear combination of these elements. So, we transform this and make some simple calculation, and we are arrived at system of equation in Ki is non-homogeneous system in terms of K. So this is a augmented matrix. So we have to find either. So we reduce this into row equivalent form. That is, we use echelon or reduce echelon form and reduce it into some row equivalent form. So in that case, you can see over here, here we have one free variable, and or also in that case, the zero is equivalent to this constant, which says that the given system is inconsistent for um, values of A, B, C, because the if you can see over here, the rank of this matrix is 2, whereas the rank of the coefficient matrix is 3. So in that case, dear student, if you can look over here, the both the ranks are not same. So in that case, we can say the first condition is not fulfilled, which is either they form a basis for span these vector 1 to basically 1 1 2 1 0 1 2 1 3 span the R3 or not. So these vector given in this example, like here this vector does not span R3 because the condition is not satisfied. So okay, in that case, since the ranks of A is 3 and rank of AB is 2, in that case, if you can solve this. this reduce this in term of ki's, then one ki must be depend upon other ki's. In that case, ki's values are not only depend upon a b c, but also these are depend upon ki's. So if you get this, what does the rank? If the ranks are different, then in that case k1, k2, k3 values are depend upon each other. Means to say k1 can be written as a combination of k2 or k3, or k2 can be written as a combination of k1 or k2. So if in that case, if we can say this k1, k2, k3 values are only written as in term of a b c arbitrary values, then we can say these are consistent. But in that case, due to this zero, these zero row, it does not qualify for that independent values of ki's. So these are not a linear form spanning set. Let us take one another one example. So with just you can calculate determinant of this matrix. So in that case, you can also say these are not linearly independent, as well as not span R3. So this is another way to find whether it is form a basis for R3 or not, because basis satisfy two condition. One is linearly independent, and second one is spanning. That basis span the vector space R3. So let us take one another example, that we have four vectors v1, v2, v3, v4 form a basis for vector R3. Dear student, if you can write it in the form of, say, set, let me, if you can give me some space, if I can write it down S, uh, which is consist of like V1, like this is V1, comma, this is V2, and comma, this is V3, comma, V4. So if you can write it down over here, this is V2, and this is V3, and this is V4. So in that case, and V1, V2 are explicitly equivalent to these conditions, like these values. So uh, let us come up with this. So if S is V1, V2, V3, V4, and V1 is 3, 1, 1, 4, and V2 is 2 minus 3 5, v3 is 5 minus 2 9, and v4 is 1 1. So dear student, if you can realize these corollaries of last theorem, like this one, if you can go back to your slide number, let's say this one. So dear student, if you can realize the corollary, like k is greater than n, then the vector given in this n set is linearly dependent. What does it mean? Because the uh, length of the vector is greater than the length of the mm, basically power of your vector space, or tuple number of uh, uh, vectors in vector space. So basically that only qualify for, if this condition prevails, then these vector will qualify for linearly dependent set. So let us elaborate this with the help of example. Rather solving this example completely, you have to just utilize this statement of this theorem. This is the one of the beauty of that theorem. So let me elaborate this one. So, dear student, like this one, you have V1, V2, V3, V4. So, in that case, K is 4 and N is 3. So, K is greater than 4 is greater than 3. In that case, you need not to be solve this whole system because these are linearly dependent vectors. So, you need not to be solve all this. So, we just shut down this example over here. So let us, if you can solve this, even then you will get quite different things. So let us, if I just solve it all, if you can solve, even then you get the rank of coefficient matrix is 3 and rank of augmented matrix 2. In that case, even then you can see over here there is a one whole row is 0. In that case, there will be a one free variable. So all ki's values should not be independent. These are depend upon some other KIs. In that case, dear student, if you just solve this whole example like as I did, so in that case, even then you get linearly dependent set. But I just used the previous theorem, corollaries of previous theorem, which is available on slide number 5. So I just sum up that k is 4 and n is 3. So k is 4 is greater than 3. In that case, the statement of corollary 1 on slide 5, I have utilized it and so to draw my conclusion that this set is linearly dependent. So this does not form a basis for the vector space R3. So there should not be you should not calculate all this stuff on available on slide number say 17 and 18. So determine whether these set form a vector space for R3 or not. So dear student, once again the vectors are greater than the power of vector space. So in that case, once again, this is a linearly dependent set. So if you can see over here, so they form a basis, but actually they are not linearly independent. So I just plug my theorem that is available on slide number 5 over here. That in that case, if you can even reduce this matrix into echelon form, so even then you get some non-zero values of ki for if you can transform the if you can put v1 v2 v3 over here and you will get a system of equation three equation and in four unknown. So I just put it in augmented form a matrix. So this is homogeneous system of equation. So when you solve this, so you will get k1 is 1 over 39, k2 is 16 by 39 and K3 is 17 by 39. But what about K4? So in that case, K4 will be a free variable. So if you can uh, solve, even then you will get the dependent uh, uh, vector. So if I can solve the this is a not theorem. This is just a corollary of theorem available on slide number 5. Here, a number of vectors are greater than number of power of vector space. So k is greater than that case S, which is basically consists of four vectors, and that is basically the S consists of four vectors. So in that case, these vectors are linearly dependent. So dimension of vector space is the number of element in a basis is called dimension of vector space. So if I say this is a subspace of any vector space R square, you should not be confused. If you can take the very small, any small set of R square, since the vectors given in S are linearly independent and also span R square, thus it form a basis for R square. So the dimension of S is 2 or dimension of S square is 2. Also dimension of Rn is n. So in that case, the number of vectors available in basis set, because this is a basis, because it satisfies two properties, because these vectors are linearly independent, also they form a span of R square. So in that case, the dimension of S is 2. Uh, dear student, if the dimension of any vector space is finite, in that case we can say this finite dimensional vector space, and if the dimension of vector space is infinite, in that case we can say it is infinite dimension vector space. So dimension of m cross n matrix, our real number is m into n, and dimension of Pn means the polynomial of nth degree is n plus 1. A vector space, okay, I have discussed this finite and infinite dimension vector space. Thank you all, dear student, for attending just for this lecture. And please stay at home. May Allah bless you all, and keep in touch. And if you have any problem regarding basis and dimension, please do ask. And if I can advise you, then please go through from your lecture of base spanning and in linearly independent set. Then you have to take this lecture of basis and dimension. That will then you will exactly understand what does I means the basis of any vector space. So while I'm saying basis, we basically if we impose the condition of linearly independent on spanning set, that it means we reduce the number of element in order to generate a very large vector space. So dear student, this is the concept is more or less related with the minimization of length of any subset of a vector space in order to generate that larger vector space. So till then, Allah Hafiz, and may Allah bless you all.